Okay, let's look at another problem from 6C. So we have the number of ants in a colony after T months is modeled by, and then we're given this function. Step 1, sketch a graph for the function. Okay, so just in graph mode, we have 25,000 divided by, in brackets, 1 plus 4e to the power of minus t, or minus x in our case. Okay, close the bracket and graph it. Now, we're dealing with quite a large number here. Obviously, we've got 25,000, okay? So that's going to be change my V window to have a maximum value of 25,000. And we're only talking about this circumstance when time is greater than 0, which means our x minimum only needs to be 0. All right, let's have a look at what this looks like. Okay, good. Let's increase our x maximum to about, let's say 12. Let's double that. Okay, so this is what the type of function we're getting. Okay, identify the type of model. All right, so we've drawn a sketch of the function. That is done. So let's identify the model type. Well, let's look here at on page 218. And here we've got a list of all of the different types of models that we have. Okay, so we've got the logarithmic model, the surge model, the terminal velocity model, and the logistic model. Okay, just looking at the graph, which one does this most likely resemble? Okay, it has similarities between the terminal velocity and the logistic model. Okay, so we could further investigate this graph here to determine the difference between these two. And there's a very fine difference. Okay, terminal velocity model has no turning points or points of inflection, and it's function is always increasing, and the rate of change is always decreasing. Okay, note the differences here for the logistic model. Function is always increasing. Okay, but there's a point of inflection here at C on 2, and they're both asymptotic to y equals a or y equals c. Okay, in the case of the logistic model, c is the number at the top. In the case of the terminal velocity model, a is the number at the front. So if we look at our original function then, 25,000 on 1 plus 4e to the minus t. Which one does this more closely resemble? It's a logistic model. Okay, so identify the model type, logistic. Okay, identify the initial ant population. Okay, this occurs when t is 0, yeah? E to the power of 0 is 1, 4 times 1 is 4, so we have 1 plus 5 is 5, 25,000 divided by 5 is 5,000. Okay, so you can do it manually, or from our graph, we can g-solve it. Let's find out what the intercept is. When x is 0, the y-intercept is 5,000. Okay, so with this population or colony of ants, there's originally 5,000. What is the ant population after 3 months? Okay, to do it manually, put 3 into the equation, or again, we can g-solve. Okay, this time we're calculating y given x. X is equal to 3. All right, 20,848. Is there a limit to the population size? If so, what is it? Okay, so let's look at the function. Obviously, this function is asymptotic to whatever this number is here. If we can remember from our logistic model, okay, y equals c is a horizontal asymptote, c is the number at the top, okay? So what is the maximum value that this function can reach? Well, it can't quite reach 25,000, okay? It can get infinitely close to it, but never reaches 25,000. So is there a limit to the population size? Yes, there is. It's 25,000. All right, there will never be 25,000 ants. At what time does the population size reach 24,500? Okay, this is another g-solve. Okay, only this time we're calculating the time. Okay, so we're doing an x calc. We're putting in a value for y. Our y value is 24,500. Okay, so it occurs when x, or when the time is equal to 5.27. So at 5.27 months. Okay, find the derivative of this function. Now this can be a little bit difficult, but I'll show you what we're doing here. So we have the original function, at equals 25,000 on 1 plus 4e to the minus t. Now, one of our index laws, okay, is that if we have 1 on a, we can write this as a to the power of minus 1. Okay, and that's exactly what we're going to do here. We're going to pretend this whole thing on the bottom is a. So we leave our number out the front, 25,000, and we're timesing that by 1 plus 4e to the minus t to the power of minus 1. And now we can easily find the derivative of this function. Okay, we have to use the chain rule. Okay, so let's let u equal 1 plus 4e to the minus t. Then a is equal to 25,000 times u to the power of minus 1. Okay, so if we're talking about the derivative of this with regards to u, all right, it's going to be minus 25,000 u to the power of minus 2. Okay, now if we're talking about the derivative of u with regards to t, remember this is our u function here. All right, derivative of 1 is just 0. Derivative of e to the minus t is going to be minus e to the minus t, and we have 4 lots of that. So du on dt is minus 4 e to the minus t. So therefore, a dash t is going to be this function times this function. Okay, this part here is dy on du, and this part here is du on dt. Okay, and what we're doing is figuring out what dy on dt is, or the derivative of a. Okay, so this is equal to minus 25,000 times u. Now u is 1 plus 4e to the minus t. Good. And that's to the power of minus 2. And then we're timesing that by minus 4e to the power of minus t. Okay, so we can do some clever manipulation here. Okay, firstly, let's just multiply these numbers. Minus 4 times minus 25,000 is minus 100,000. Sorry, is positive 100,000. Okay, and let's leave this e to the minus t here. Now, all we have on the bottom then is this part here. Okay, and of course we can do that. If we have a to the power of minus 2, we can write it as 1 on a squared. So that's what we're doing. We're putting it as a denominator. 1 plus 4e to the minus t, and that is squared. Okay, done. Find the time when the ant population is maximized. Okay, so the maximum ant population occurs when dy on dt equals 0. Okay, so that means this function that we've calculated here is equal to 0. All right. When does this occur? Okay, well, it doesn't. Okay, if we were to solve this, this is what we'd do. We're going to times both sides by the part that we have at the bottom. Okay, so that's going to cancel on this side, right? We're doing that times both sides. Okay, so then we're going to have the top part being equal to 0. Okay, but of course we can never have e to the power of t being equal to 0 because it is asymptotic to the x-axis. Okay, so therefore maximum point never occurs. Okay, and if we look at our interesting points about the logistic model, If the function's always increasing, then it's not going to have a maximum point. Okay, it gets close and close and close to 25,000, but never quite reaches that value. All right, so you should be working through. You should easily finish 6C. Okay, basically you get to use your calculator for it. The hardest part will be finding the derivative of some of these functions. Okay, and if you can't do that, that's fine. We'll just practice that, and you'll get good at it. Okay. So you're definitely going to want to finish 6C and 6D. All we're doing in 6D is looking at the shapes of functions and just judging by the shape, what type of function could that be. So if we look at this one, well, that's approximately linear. Okay. If we look at this one, well, that could be a quadratic. That could be a cubic. This could be a terminal velocity function. All right. So we're just looking at what do these functions look like. All right. What about this one? Definitely a surge function. All right, we're just looking at what do they look like. Well, it sort of resembles this. It's a possibility. This one is a possibility. Okay, and some of them may have multiple answers. Okay.